Welcome to Part 4 of an insecticide mode of action series developed by Burris Seed. This is Matt Montgomery. I'm the sales agronomist here at Burris, and today we're going to talk about neonicotinoids. If you've forgotten what neonicotinoid insecticides are, think about some of our more common insecticide seed treatments. We've started just about every lesson in this series by talking about the nervous system, by reminding you how the nervous system works, and then describing how a specific family of materials messes up the nervous system. We've also started every one of these sessions with a disclaimer, and we'll do so again here. If you have not watched Session 1, our primer on how the nervous system works, please stop what you're doing and watch that session first. As with any mode of action topic, be it fungicide, herbicide, or insecticide, this topic can get pretty deep, and we want to make sure you don't feel like you're drinking out of a fire hose. With that, let's get started. Now, as you may remember, the brain initiates a signal that's supposed to tell the insect's body something important that needs to be done. So it will say breathe, or move, or flex your body and pump your blood around. Things that are important for the insect to stay alive. That signal travels down a nerve, but that nerve is actually a series of neurons, nerve cells. Each nerve cell has a gap between it and the next nerve cell. The nerve impulse moves through the cell, across that gap, and onto the next cell until the signal finally reaches its destination. At that point, the insect breathes or moves or flexes its body to move blood around, etc. Now, when we apply an insecticide, we're shutting down that signal that moves from one cell to the next. I guess in effect, we're chemically severing the flow of information down that nerve. The brain says what needs to be done, but the signal never reaches its destination. So the insect dies because its body isn't ever told what needs to be done. Now, how this disruption occurs is linked to how the nerve cell actually works. We previously said that the nerve cell looks like a tree. The branches are the top, where the signal comes in, and those are called dendrites. The trunk, the middle part of the cell through which the signal moves, is called the axon. And then the signal eventually reaches the roots, which we call terminal branches. And here, the electrical signal that's been moving around inside that cell is converted into a chemical signal. Now we're going to run through this quickly so we can get to our topic, but remember that the root of one neuron is butted up against the branches of the next neuron. That little black dot that you see is a chemical key, a chemical signal, and it does what a key should do. The key is intended for a door or a gate in the next neuron, and it will open it. So it inserts itself into the door, and it opens that door. Because the charge inside is different than the charge outside, positively charged sodium particles rush in and change the charge. Now when that happens, the inside of the nerve cell goes from negative to positive, and you've successfully caused this next nerve cell in the line to fire. You've successfully sent the signal to the next neuron in the chain. Now, if the door does not close, that cell will keep firing. So the nervous system releases another chemical that chews up the key. When the key has been metabolized, the doors, the gates shut. The neuron then reverts back to its normal state, a negative charge, and the signal stops firing. If we disrupt any part of this delicate process, we disrupt the flow of information from one neuron to the next. In effect, we can use this delicate nature of the nervous system to chemically sever the brain from the body. The topic of neonicotinoid insecticides is linked tightly to the discussion we just had. This delicate process of chemically transferring a nerve impulse from one neuron to the next is what neonicotinoid insecticides mess up. Let's take a moment to briefly mention how important these materials, neonicotinoids, are to modern agriculture. Neonicotinoids really only entered commodity production around the turn of the century. I'm talking about the turn of the 21st century here. At that time, a host of subterranean insect pests occasionally plagued fields, and once the damage was done, there was no rescue treatment. So think back to grape colaspis, wireworms, grubs, etc. When these materials were introduced, early season problems with those kind of insects, which often resulted in a replant, literally disappeared. Today, stand reduction from subterranean insect pests is pretty rare. Now, there are some environmental concerns that have developed in relation to the use of neonicotinoids and their potential impact on bee colonies, for instance. So the industry is working on dust-reducing products. It's to our benefit to minimize any off-target impact associated with these pesticides because they have really been an invaluable addition to our industry. They're a great resource. Back to the subject of mode of action, though. These products, things like Poncho, Cruiser, etc., act like skeleton keys for the doors of the neuron. In other words, they fake out the nervous system into opening those little gates that are only supposed to open when a legitimate chemical signal is being sent. You know what happens next. Because the gates are open, even though they're not supposed to be open, even though they are not open for the right reasons, positively charged sodium begins to rush inside. The charge changes inside the cell. The cell fires, but there is one problem. The cell is not supposed to be firing. The cell is firing when it's not supposed to be. That alone is a very bad thing. However, the next part of this scenario gets even worse. The chemical that was designed to chew up those legitimate keys for the door so that the door can close and the cell can go back to normal, well, they're designed to chew up the legitimate keys, not the illegitimate keys, if you want to call it that. That means they can't chew up the neonicotinoid skeleton key, and that means that that neuron just keeps firing and firing and firing. That wasn't enough on its own, though. Did you notice what was also happening while the neuron went crazy like this? A legitimate signal, so this signal to breathe or to move or to flex and pump blood around, was being sent across the gap. When it got to the keyhole in the door of the next neuron, what did it find? It found that the neighboring keyhole was already occupied by this blasted skeleton key. Now it just sits there with no place to go. So let's stop and think about what happened here. The nervous system went crazy when it should not have. It's like the telephone line was full of static, but worse yet, the old skeleton key stopped the transfer of a legitimate signal. It stopped the nerve impulse dead in its tracks. It used different mechanisms to do exactly what we talked about before. It chemically kept the brain from getting information to the body of the insect. It causes the nervous system to act as though there is not a nerve connection between the body and the brain. So there you have it. Neonicotinoids, one of the most important, I would say, insecticide families currently at play in production agriculture. We hope you've enjoyed watching today's sessions on these products. Most importantly, we hope you're beginning to realize how delicate these tools actually are. Not only is the nervous system delicate, but the mode of action, how these things work, how these materials work, is delicate too. It's very easy for resistance to develop, and it's therefore critical that we manage these resources. Well, thanks for watching, and stay tuned for more information from Burris Agronomy U.